So a Faraday cage is basically a screen that keeps RF out. It's a way of shielding an object or maybe stuff on the outside to keep RF out of it. So this is a Tesla coil, very high voltage at the top, also a very high frequency, and it's creating this bolt of lightning that comes down. It's a big arc, and he's inside a Faraday cage, and this guy right here is not being affected by the bolt of electricity. Generally with a Tesla coil, this is very low amperage, and it'll do some interesting stuff, but it'll pass right over the surface of your body. And Tesla used to stand on the top of his Tesla coil and have these bolts of lightning coming off of his hands, and people would freak out.
His hair would stand up.
But it's really pretty harmless. So a Faraday cage can be a screen like she's showing. Yeah, or like this over here. Your microwave oven is a Faraday cage. For you, it's keeping all those electrons from the microwave from getting out into the kitchen. So what about this one right here? That looks like a rabbit cage. So at what frequency would this be a suitable Faraday cage? Would it be okay to use at microwave frequencies?
Not one of those things.
But I don't know. More than likely, if you got higher than your low microwave range, like say you put your Wi-Fi router inside there at 2.4 gigahertz, wouldn't do anything at all. Go right through it. Because that 2.4 gigs, that wavelength is so small that those openings would be like a big window.
Yes, it's
Go right through.
transparent.
Well, you can actually do the calculation, right? Because the gap between the wires is roughly about an inch.
Yeah.
And you can figure out what wavelength is going to be smaller than that.
So a half a wave is what they consider necessary.
And here's where the problem with that
has to
comes
be
in.
less than a half a wave.
Here's where the problem comes in with that. Does anybody know what the wavelength of an EMP is?
It's very low.
It's a square wave. There's so many different wavelengths in there. It can be anything.
Okay. Oh, and they showed a trash can right here. That's a very nice pair.
That's a really good way to go.
Yeah, that's probably as good as you can get.
But you gotta remember when you insulate it from the can inside.
Yes, you do. Everything has to be on insulated standoffs or fiber insulation or something to isolate it from the can.
So, coronal mass ejections. I wish I had a video of this, but if you go on solarham.com, usually they're showing a recent flare, and they might have a mini movie of about 10 seconds that shows the blast of a coronal mass ejection coming off the surface of the sun. It really is impressive. Ejection of large amounts of material from the corona, a continuous stream of charged particles that comes maybe in the direction of Earth, not always. So most of these that we see are coming off different parts of the sun, the top and the bottom and the sides and the back. Well, most of them are not aimed directly at Earth, and they're expanding out and cover a lot of area. Maybe the edge of it will hit Earth. We see a little bit of aurora. It's when one is directed right at us that we have to worry about.
For the test, that statement right there, that definition, CMEs is coronal mass ejection, will likely be on your test.
So the solar
This
wind
statement will likely be on your general test.
affects radio propagation over 15 hours to several days later. So often these are kicked off by a flare, and a flare will have immediate effects. Well, not immediate, 8 minutes later. It takes 8 minutes for light to reach the Earth. So the CMEs are often associated with solar flares. Particles become trapped in the Earth's magnetosphere. So yeah, the coronal mass ejection takes a lot longer to get to Earth than the flare. The flare is going to happen in 8 minutes. A coronal mass ejection might take days to get
It's
here,
ionized
depending on
particles.
how much oomph it has.
It's separated electrons and protons and neutrons that are ejected from the sun, and they physically have to travel.
Right. So solar disturbances, high latitude HF propagation is greatly degraded with geomagnetic disturbance. What do they mean by geomagnetic disturbance? Okay, more flare activity, more variability in the output of the sun. You got more sunspots. The magnetic field gets more distorted, and what we see on Earth is more noise and more variability in the signal strength. In general, there's a lot of places where you get a prediction for the geomagnetic disturbance. And when it's low and the sunspot cycle is high, oh man, you're golden, because now propagation is good and the noise level is low. Auroral activity can be increased with solar wind when it's high. Signals modulated with a hiss of a buzz when you've got geomagnetic disturbance, and there's a visual example. I wish we were in a location where we saw more aurora.
Yeah, me too.
We do see them here, but they're
Just a
rare.
glow.
Yeah, it's just we're just not in a good position for the aurora.
What you're actually seeing there is the magnetic field of the Earth and those energized particles interacting with that. So you're actually seeing stuff from the sun entering the Earth's upper atmosphere. And it's just like a fluorescent light or a neon light.
It's like a neon. Yeah.
It's actually about the altitude of the elater.
There's the Aurora Borealis and the Aurora Australis. And it's not just planet Earth. If another planet like Jupiter has a magnetic field, which it does, you see aurora at the poles of that planet as well. That's an example of a sunspot. So sunspots are just cooler zones. Imagine a pit of a swirling vortex of magnetic field. And it's literally creating this pit of cooler gas on the surface of the sun. So when we look at it, we're looking down into this vortex of magnetic field. And they can be pretty big, bigger than the Earth. Occasionally, when they're that big, they're naked eye. If you have a little solar filter you can hold up, you can literally see it with your naked eye. Something that big with your naked eye.
And the Chinese have been recording these for
Yeah.
centuries. Oh, yeah.
They emit UV radiation that ionizes Earth's atmosphere and allows us to refract signals off the ionosphere. So, lifespan of less than a day to a few weeks in sunspots. They are somewhat stationary on the Earth's surface, but they appear to move because the sun rotates. Okay, they appear to move because the sun rotates on its axis. It rotates about every 28 days on average. It actually moves a little faster than that at the equator, a little slower than that. So you might have a whole bunch of sunspots that are producing some really great conditions for HF propagation, and then within a week and a half, 2 weeks, it's gone. What happened? Well, those sunspots are rotated around, and they may persist for another rotation. 400 years of sunspot observations, and there's a lot of variation in there. Back in the 1600s, 1700s was the modern minimum, where sunspots virtually disappeared, and that was also a cold period. You know, some say we're in for another modern minimum. There was a smaller minimum, the Dalton minimum right there, but recently we've been seeing a maximum. During the International Geophysical Year back in 1957, we saw the highest high point, and we thought, wow, maybe this is the way it always is. Maybe it's going to be like that. And no, next cycle it was way down. Next few cycles came back up again, and it went back down again. So right now we're in a trend. It's trending down. So although we're looking at good conditions for the next couple of years as we ramp up, it's not going to be as high as the International Geophysical Year was.
As much as half of the population of the Earth starved to death during the modern minimum. Food production went way down.
High numbers of sunspots, high ionizing radiation, sunspot activity follows the 11-year cycle. And that, again, it's an average.
It's approximate.
At the peak of the solar cycle, ionization levels can be high enough that 6 and 10 meters stay open and make long-distance communication possible. I'm waiting. At minimum, bands above 20 meters may not be open at all. In fact, 20 meters may just open at midday. I saw this in the last cycle.
Yeah.
At the bottom of the cycle, 20 meters would open up for like 2 hours midday, and then it would die again. That is typical. That 20 meters is usually the go-to band for DX
Daylight hour.
in daylight. At the peak of the sunspot cycle, 20 meters will be open day and night, all day long. And that might be the maximum usable frequency in, after midnight, but God, you get some great DX.
And the Earth's atmosphere actually expands when it's energized. When the sun's putting out solar wind and lots of electronic magnetic stuff is happening, this atmosphere actually expands over 50%. So it affects things like satellites in orbit and all kinds of other things.
Okay, strong seasonal variations. Seasonal variations due to different levels of ionization, summer and winter. Of course, in the winter, the ionization level will be lower. Seasonal variations on lower bands due to high levels of atmospheric noise or static in the summer months. You're going to see more static in the summer months. Why? Because you got thunderstorms, and thunderstorms produce lightning. And that lightning, you'll see in your S meter as a whack, whack, whack. In the S meter per second, and then drop back down again. Daily variations due to different levels of ionization between day and night. It's going to be less at night than it is during the day. Measuring solar activity, you have a sunspot number where they actually count all the little tiny sunspots. The higher number generally indicates a greater probability of propagation. Sunspot number equals 10 times the number of groups plus the number of sunspots. So it's a calculated equation. It's not the exact number that are visible.
Yeah, if it's 35, you're not going to see 35 sunspots.
The average of observations from many different locations are all collected, and what you see on your website will be the calculated sunspot numbers. So from that, they developed the Solar Flux Index, a measure of solar radiation with a wavelength from 10.7 centimeters. This follows very closely the sunspot number. So when the sunspot number goes up, Solar Flux Index goes up. And indicator of UV radiation, and UV radiation, of course, is what ionizes the upper ion.
Okay, stop, Steve. SFI is always solar flux index. Sunspot number is always SSN. One or the other of these, as well as this statement or this statement, is going to be on your test.
Okay, so just for your information, right now the solar flux index is around 130, 127, something like that. And that follows the sunspot number pretty closely. At that level, we're not getting great propagation. We want to see that solar flux index around 160 to get some really good propagation, but that's just for your information. The K index is a measure of the short-term stability in a geomagnetic field. So we're not talking about what would cause good propagation, we're talking about what gets in the way of good propagation, and the stability is one of it. That if it's unstable, you've got a lot of variation, you've got a lot of noise. So the minimum value is 0, maximum value is 9, updated every 3 hours. Higher values equal poor HF propagation. 15 meters, 12 meters, and 10 meters are the least reliable bands for long distance communication during periods of low solar activity. And the reason for these higher bands being the least reliable is because this skip frequency is above the maximum usable frequency. Measuring solar activity, there's an A index, measures the long-term stability of the Earth's field, again, 0 to 400, calculated from 8 K index values. higher values than for poor HF propagation.
K index is every 3 hours. The A index is 8 K indexes. So 8 times 3 is 24 hours. So the K index is calculated every 24 hours. The A index is every 3 hours. That's right, and that's backward.
Wait.
K index is 3.
Yeah.
The A index is 24.
Yeah. So Northern California DX Association partners with the International Amateur Radio Union to operate a worldwide network of 18 beacons on these frequencies. They send call signs at 22 words a minute, followed by 4 1-second dashes. Call sign at 1 dash is at 100 watts, second dash is at 10 watts, third dash is at 1 watt, and the last dash is at 1/10 of a watt.
So depending on how many dashes you can hear on any one of those frequencies, you can tell just what your propagation looks like.
And what you're likely going to need in terms of transmit power to make that happen.
Yeah.
One way to determine current propagation is to use a network of automated receiving stations on the internet to see where your transmission is being received. Many of these listening stations are connected to the internet. Yeah, that's using the Whisper network, and that works really well. Solar disturbances, a solar flare, a large eruption of energy. This is like a flashbulb going off on the surface of the sun. It's really intense, very bright, and very quick.
And very powerful.
Caused by disruption to the Earth's magnetic field, Sun's magnetic field. It takes about 8 minutes for the energy to reach Earth, so it's just like light. And there's an example of one. That bright area in the far right of that image is the flare itself. You've got this prominence blasting off from the sun caused by that flare. This is a coronal hole. That whole dark area, that's a huge coronal hole. And if that were right in the middle, then the solar wind would be coming right towards Earth. In this case, it's on the limb of the sun, and it's going away from it.
So
There's a weak area in the corona through which plasma can escape the sun's magnetic field and stream through space at high velocity. Charged particles that reach Earth usually disturb the HF communication. I wish I had a motion picture of this. As those charged particles hit the Van Allen belt and our magnetic field, it gets distorted around the magnetic field. So the magnetic field is protecting most of the Earth. And a good proportion of those charged particles come in through the field lines of the North and South Pole, and that's when we see aurora. So a solar disturbance, a sudden ionospheric disturbance, that's in the Earth's ionosphere, is a SID. UV rays and X-rays from solar flare travel to Earth at the speed of light, and that's the speed of light. They reach Earth in about 8 minutes, greatly increases the ionization level of the D region. Remember when we said the D region was the lowest one? And when that saturates, not much gets through. 80 meters begins to go away because it gets absorbed. Well, under really high ionization, everything gets absorbed. 20 meters gets absorbed, 10 meters gets absorbed. Nothing gets out.
Airplanes aren't able to use their radios even.
Yeah, it's pretty weird. I was in a field day in California when we had set up, we had the generator working, we're working stations, and all of a sudden,
Everything went dead.
nothing. Everything went blank. Well, the generator's still on, the radio is still on. What the heck? We had just had a solar flare. For the next 40 minutes, we didn't hear anything. It was really weird. And slowly the signals came back. It disrupts signals on lower frequencies more than those on higher frequencies because it's energizing that D layer, and the D layer is more effective on the lower frequencies. So yes, if it's a really weak flare, it only meant a few seconds, few minutes. Generally, you see it over in about 20 minutes to half an hour, but it can last longer than that. We had a good one just the other day that lasted an hour or more.